Hi, my name's Alex Brinkmeyer, and today I'll be presenting to you some work on the effects of temperature on ultra-thin composite space structures. This work was done at Caltech during a recent placement. So just to give you a bit of a background on what this entails, this is the nanosail D. So this is a small-scale solar sail. And the sail is deployed by four central spring-like structures. So the deployment of this structure is critical to the success of the mission because you only get one chance to deploy this. So I'm just going to give you a quick video background on this project and see how it fits into mine. So this is basically a short video by Discovery Channel on the NASA sail. So it deploys using this system. So the whole sail is enclosed into this small structure, and at some point during the mission, the flaps are opened, and four central tape spring structures unfold from the structure. You'll see this in a second. So here you go. So basically, these four structures entrain the sail as they open from the flap. They basically release the sail from a central spindle as it unfolds. So you can see the deployment in motion. Okay, so recently another mission called the Mars mission. So this mission was designed to investigate the atmosphere of Mars using this radar. And the deployment of this radar was subjected to some stowage conditions on ground. And during the release of the structure, some delay in the deployment was experienced, and the latching of the structure was not complete. So it's really important to understand how these structures behave on ground prior to release in space. So the objectives of this presentation is to study the effects of this stowage on the stability of these structures called tape springs. Also measure the deployment rates for various stowage conditions and see the effect of temperature on that deployment. And also model the effects of stowage on the deployment using an analytical model. So if we look at the typical tape spring geometry, the structure that drives this structure during its deployment, it looks like this. So it starts from a coiled structure and it deploys out in a single rolled structure. So this is characterized by several entities. So the coiled radius here, which is little r, and the large uncoiled radius, so large r. So what we use for this structure is a thin ply carbon fiber prepreg. So this carbon fiber basically has extremely small thickness. It's 30 microns in thickness. And these are the properties that have been determined using instron tests at room temperature. And for this structure, we use this antisymmetric layup, which is shown as follows. Now, the use of an antisymmetric layup is needed to reduce some bend twist effects during the deployment of the structure. So how we model the structure is detailed as follows. We first start with a relaxation model. So this is designed to model the viscoelastic effect. So the relaxation effects of the structure when it is stowed on ground prior to deployment. So once the output of this model basically is the ejection force of the structure. So the ejection force will determine how the structure unfolds. And then we have a second model which basically models the deployment of the actual structure. So the material model we use is called a Prony series. It's basically a sum of decreasing exponentials. And in order to characterize these coefficients here and there, we need to undertake experimental tests. So these experimental tests use DIC cameras. So this experimental test was conducted at Caltech. So DIC cameras plus a thermal chamber, which controls the temperature of the specimen. And these are the results of the test at 60 degrees. We have basically a relaxation of the modulus. So this is the transverse modulus of a laminate, of a 6-ply 0-degree laminate. So this is basically to understand how the transverse modulus relaxes with time. We just assume that the longitudinal modulus is constant as it acts in the fiber direction. And we fit to this experimental data the Prony series that I showed you previously. So you basically get about 35% decrease in modulus after 3 hours of relaxation. This is 3 hours, 10 to the 4 seconds. Now, the ejection force is modeled using the following model. I'm not going to go into too much detail. An ejection velocity is simply determined using a kinetic energy balance and is shown as follows. So if we go into the results, the ejection force decreases similar to the transverse modulus, so you get a strong decrease with time. This is shown for 60 degrees at 3 hours. Now, this was the relaxation part of the model. Now we're looking at the deployment. In order to test the deployment, we first coil the structure into its cold states. Then we stow it in a thermal chamber, and then we finally deploy it on a flat surface. So when we do not have any stowage, so when we deploy it immediately after it's coiled, this is what we get. And the analytical model follows relatively well the experiment. So we get a smooth unrolling of the structure with time, and you can see that deployment is achieved in this case after about 0.4 seconds for a 1 meter structure. So this is how it looks like in reality. So you get, so the deployment in this case is manual because of the short time constraints we had, but you can see that deployment is relatively smooth and fast. Now if you look at a case where you apply stowage, what you see is an increase in the deployment time, as you would expect because the ejection force has decreased. You can see that also that the analytical model does not match as well the experiment, but this can be refined later to incorporate other models. What we also get is an interesting case is when you deploy the structure, you initially get a period of static, it's basically a latent behavior. So you first get no deployment, and then you get the fast deployment as predicted. And this is not currently predicted by our model. So I'll show you both cases. So this is a normal case, but as you can see, in the main window here, you have the case with relaxation, and in the inset window, you have the no relaxation. You can see the delay in deployment, and you can see that this arrives much later than the case where no relaxation is applied. Now, in this case, what happens is you have a latent behavior, so you have a delayed deployment, and this might be important when you consider a space deployment where you need an immediate deployment. This might be interesting to take into account. Now, what happens if you stow it for very high temperatures? So in this case, we stow at 100 degrees for 3 hours. And you get a very particular case, which is not predicted by theory in this case, is that, well, there is no deployment at all. So the structure fails to deploy, and this might mean that you lose your mission in this case, because you have a behavior which is completely unexpected, and you're relying on autonomous deployment, whereas in this case, you get none. So the conclusions of this study is that, well, you do not have any self-deployment of the spring during the stowage period, that the deployment time increases for a higher stowage time and temperature, but also more crucially that you have what you might call deployment failure at high relaxation times, and this needs to be taken into account into the design of future space structures. Finally, the analytical model needs to be refined for higher values of relaxation, as you could see that discrepancy increasing for those high values. So in future work, we could implement maybe a numerical model to include 3D effects, improve maybe the material models, and possibly also consider other layups. I'd like to thank my partners. Thank you.